The 8 engine killers hiding in your oil change. Most people treat an oil change like doing the dishes. Drain it, refill it, call it done. But what if the moment you twisted that drain plug was the moment you started killing your engine? And you had absolutely no idea. A landmark study published in 2024 by SAE International tracked thousands of engine failures across multiple vehicle platforms and found something that should terrify every driver on the road. 37% of all premature engine deaths were directly tied to mistakes made within 72 hours of a routine oil change. Not defective parts, not bad oil, not worn gaskets from age. Post-change procedural errors. The kind of errors that look like nothing at all until your engine seizes on the interstate at 70 miles per hour. The 8 mistakes you're about to hear aren't theoretical. They're backed by engineering data, lab analysis, and real-world case studies. Piston rings, rod bearings, camshaft lobes, valve seals. These precision components are being silently destroyed every single day by drivers who genuinely thought they were doing everything right. No warning lights, no smoke, no sound. Just gradual, irreversible mechanical damage accumulating beneath your hood. If you've ever changed your own oil, had it changed at a quick lube shop, or plan to do it yourself in the future, this video could be the most important automotive content you ever watch. Before we break it all down, if you're not subscribed yet, hit that button right now. We publish in-depth automotive engineering content that most mechanics won't explain because informed customers don't bring them as much repeat business. Subscribe so you never miss it. Now let's decode all 8. Mistake number 8, the double gasket time bomb. This failure mode shows up in roughly 1 out of every 12 DIY oil changes. It produces 0 symptoms for the first 100 miles, and then it accelerates toward catastrophic engine failure with almost no warning window. Here's the mechanical sequence. When you unscrew a used oil filter from the engine block, the rubber sealing gasket mounted on the filter's base doesn't always come away cleanly with it. Because the filter sits in a recessed mount and the gasket surface is coated in a thin layer of hot oil, the gasket can peel away from the filter flange and stay stuck flat against the block. It's nearly impossible to see with a casual glance, especially in a dimly lit garage or when you're working under a vehicle that's still dripping. You then thread on a brand new filter, complete with its own fresh gasket, and you've just created a double stack seal. 2 rubber rings trying to seal the same mating surface against pressurized oil. Neither one seats correctly because the mating geometry was designed for a single gasket thickness. The result is a slow, progressive leak that starts as a few drops pooling overnight in your driveway and escalates fast. In a documented 2022 case study involving a Honda Accord, this exact scenario caused 2.3 quarts of oil loss in under 400 miles, starving the camshaft bearing journals and resulting in complete bearing failure. A repair bill north of $3,800. The prevention cost you 2 seconds of time. After pulling the old filter, take your index finger and slowly trace a full circle around the filter mounting flange on the block. Run it deliberately, not casually. If your finger catches on a raised rubber ridge, a ring that wasn't there before you started, that's your old gasket. Remove it completely. Then install the new filter with confidence. 2 seconds of tactile inspection versus $4,000 in machining costs. There is no version of that trade-off worth skipping. Mistake number 7, the cold oil contamination cycle. There's a widespread belief that draining cold oil is just slightly less efficient than draining warm oil. The truth is significantly worse than that. Draining cold oil doesn't just leave some residue behind. It leaves a chemically active contamination layer that begins degrading your new oil the moment you pour it in. At ambient temperature around 70 degrees Fahrenheit, conventional 5W30 engine oil carries a viscosity of approximately 11,000 centipoise. To put that in context, water at room temperature measures about 1 centipoise. You're essentially trying to drain a fluid nearly as thick as molasses. That oil clings to cylinder walls, coats the inside of valve covers, saturates oil galleries behind the camshaft towers, and pools in every low point of the oil pan. When you pull the drain plug on a cold engine, you're realistically evacuating around 75% of the old oil. The remaining 25% stays behind, trapped in areas the drain can't reach. That leftover oil isn't neutral. It contains combustion acids, oxidation byproducts, metallic wear particles, and depleted additive chemistry. The moment your fresh synthetic pour meets that contaminated 25%, the new oil's additive package begins reacting with the acidic residue. Valvolane's 2023 fluid analysis report confirmed that engines drained cold showed 18% higher concentrations of silicon, iron, and carbon deposits in post-change oil samples compared to engines drained at operating temperature. The fix is simple thermal management. Start the engine and let it idle for a minimum of 5 minutes before you touch the drain plug. This brings oil temperature to approximately 180 degrees Fahrenheit, dropping viscosity to around 200 centipoise. a fluid state where the oil flows freely and carries suspended contaminants straight out the drain opening. You'll see and feel the difference. Cold oil drains slowly, looking thick and nearly black the entire way. Properly warmed oil flows rapidly, almost translucent, carrying combustion debris with it. That visual difference represents the gap between a clean system and a chemically compromised one. Mistake number 6, the overfill aeration disaster. This one is counterintuitive. Adding extra oil feels like giving your engine a safety buffer. What it actually does is trigger a mechanical chain reaction that eats bearing surfaces alive, and the damage starts before you've even left your driveway. Here's the physics. Your crankshaft, the massive forged steel component rotating at anywhere from 700 RPM at idle to over 7,000 RPM under load, is engineered to operate with a specific clearance above the oil surface in the pan. That clearance, typically around 10 millimeters, exists for a reason. The crankshaft counterweights are not designed to contact the oil, they're designed to ride just above it. When you overfill the oil pan by even half a quart, that clearance disappears. The counterweights begin striking the oil surface at thousands of revolutions per minute, functioning essentially as a high-velocity whisk. This process is called aeration, and it converts your liquid oil into a pressurized foam. Foamy oil cannot maintain a hydrodynamic film between metal surfaces, because the air bubbles collapse the moment pressure is applied. Your rod bearings and main bearings, the components that keep the rotating assembly alive, begin operating in a metal-to-metal contact state even though your dipstick reads full and your oil pressure gauge shows normal numbers. The gauge reads pressure, not film integrity. A 2021 Bosch automotive engineering study documented bearing wear rates 340% higher in overfilled engines after just 5,000 miles compared to properly filled engines. Overfilling also creates pressure spikes throughout the lubrication circuit that routinely blow valve cover gaskets and rear main seals. Expensive secondary repairs that drivers almost never connect to the overfill event. The correct approach is methodical and patient. Add oil in half-quart increments. After each addition, wait 60 seconds, then check the dipstick on a level surface. Your target is the range between the minimum and maximum marks, biased toward the upper portion, not above it. Precision here protects everything downstream. Mistake number 5, the dry filter startup. Wear window. A brand new oil filter that comes directly out of the box is completely dry inside. Every micron of filter media, every pleated fiber surface, every internal passage, bone dry. And that creates a specific measurable damage window that begins the instant you turn the ignition key. When the engine fires, the oil pump immediately begins pressurizing the lubrication circuit. But before that oil can reach the camshaft lobes, the lifters, the rocker arms, or the rod bearings, it has to saturate an entirely dry filter. During those first 3 to 5 seconds, critical wear surfaces throughout the valve train are operating with near zero lubrication film. This is classified in tribology as a dry start condition, and the damage it causes over time is not hypothetical. A 2020 study from the University of Michigan's Tribology Laboratory found that dry start events, including oil changes where the filter was installed dry, account for approximately 60% of cumulative engine wear across a vehicle's entire service life, despite representing less than 2% of total running time. The ratio is staggering. 3 to 5 seconds of dry operation causes more wear than hundreds of hours of normal driving. The pre-lubrication solution takes about 30 seconds to execute. Before threading the new filter onto the engine, pour clean motor oil directly into the center inlet port of the filter until the pleated media is visibly saturated. You don't need to fill it to the brim, you just need to displace the air and wet the internal surface. Then coat the filter's O-ring with a thin layer of clean oil using your fingertip. When the engine starts, oil pressure builds across a lubricated system rather than a dry one, and the wear window effectively disappears. Mistake number 4, the forgotten circulation check. Most drivers finish refilling the oil, screw the cap back on, and immediately take the car out for a test drive. This skips one of the most mechanically important steps in the entire procedure, and it routinely leaves engines running significantly underfilled without the driver ever knowing it. The issue is volumetric displacement. A standard automotive oil filter holds between 0.5 and 1. 2 quarts of oil capacity depending on the engine platform. When you install a new filter and pour in fresh oil to the recommended level, that entire filter volume is still empty. The moment you start the engine, the oil pump begins filling the filter from the pan reserve. Within the first 60 seconds of operation, the filter draws up to a full quart of oil out of the pan and into its media, dropping your dipstick reading by that same amount. If you immediately drive away without a post-start recheck, you're operating with oil that's potentially a quart low. According to API service classification specifications, an engine running 0.8 quarts below the proper fill level experiences a 12% reduction in oil pressure at idle and a 19% reduction under load. Those aren't abstract numbers. They represent reduced hydrodynamic film thickness at every bearing surface in the engine. The protocol is simple. After your initial fill, start the engine and let it idle for 60 seconds. Shut it off. Wait 3 minutes for the oil to drain back to the pan, pull the dipstick, wipe it, reinsert it fully, and read it clean. If it reads low, add oil in small increments and repeat. This same 2-minute process will also surface any active leaks at the drain plug or filter, and leaks that are far easier to address in your driveway than on the side of a highway. Mistake number 3, the dry seal micro tear phenomenon. The O-ring on an oil filter is a deceptively small component, typically 3 millimeters thick and 60 millimeters in diameter, made from nitrile rubber. It is also the singular barrier between 4 to 6 quarts of oil under 40 to 60 psi of sustained pressure in your garage floor. Despite this, the majority of oil changes are performed with that O-ring installed completely dry. The engineering problem is fundamental. Rubber seals are designed to compress axially under load. They are not designed to slide under dry friction against a metal seating surface. When you install a filter with a dry O-ring and hand tighten it, the rubber must simultaneously compress, stretch slightly, and rotate against the steel mating flange of the block. According to Parker Hannafin's seal engineering reference data, dry rubber-to-metal friction during installation can generate localized interface temperatures exceeding 220 degrees Fahrenheit. That's well above the threshold for nitrile rubber surface degradation. You won't see the damage immediately. The micro tears are submicroscopic at the point of installation. But once the engine reaches operating temperature and oil pressure stabilizes in the 40 to 60 psi range, those micro tears expand under cyclical pressure, loading into visible seeping leaks. These leaks are slow, inconsistent, and notoriously difficult to trace because the oil runs along external surfaces before it drips, making the source appear to be somewhere other than the filter seal. The solution requires 1 drop of oil. Before installing, dip your fingertip into clean motor oil and run it carefully around the full circumference of the O-ring until you have a thin, even coating. That boundary lubrication layer allows the seal to compress and seat correctly without the torsional friction that causes micro tearing. It takes 3 seconds, and it makes the seal last the full service interval without weeping. Mistake number 2, the stripped thread mechanical failure. Every day, drivers across the country over-torque their oil drain plugs with the sincere belief that tighter equals safer. The physics do not support this. Over-torquing doesn't create a better seal. It progressively destroys the threaded material that holds the plug in place. And when those threads fail, the plug ejects at highway speed, emptying the entire oil supply onto the pavement in under 30 seconds. Most passenger vehicle drain plugs are M14 to M18 diameter bolts threaded into the oil pan. On the majority of modern vehicles, that oil pan is cast aluminum. Cast aluminum carries a tensile yield strength of approximately 40,000 psi. The steel drain plug, however, can generate clamping forces exceeding 60,000 psi when torqued beyond specification. Aluminum loses that equation every time. When you apply excessive rotational force, the aluminum threads deform beyond their elastic limit. They stretch, elongate, and lose the ability to return to their original geometry. The first few over-torque events may leave the plug seemingly functional, but each subsequent oil change degrades the thread engagement slightly further until the plug strips completely. Repair options include a helicoil thread insert at best or full oil pan replacement at worst, a cost that routinely reaches $400 to $900 depending on vehicle platform. Ford's factory service manual specifies a torque value of 25 to 30 foot-pounds for most drain plugs across their passenger vehicle lineup, and this range is consistent with most manufacturer specifications. If you don't have a torque wrench in your toolbox, here is the practical alternative. Tighten the plug until the crush washer, the soft aluminum or copper sealing washer between the plug and the pan, begins to compress and resist further tightening. At that point, stop. The washer creates the pressure seal. Additional force beyond that point is not reinforcing the seal, it's attacking the threads. Mistake number 1, the oil life warning. Override. Every other mistake on this list is mechanical. This one is psychological, and it accounts for more total engine destruction than the other 7 combined. Modern vehicles use oil life monitoring systems integrated directly into the engine control unit. These are not odometer timers. They are adaptive algorithms that track real operating data, engine load history, cold start frequency, sustained high temperature operation, extended idle time, short trip cycles that prevent full thermal purging, and calculate the actual degradation rate of the oil chemistry in real time. When the oil life indicator reaches 0 and the service light activates, it is the ECU issuing a precise chemical verdict. The oil's total base number has fallen below the threshold required to neutralize combustion-derived acids. Acid neutralization is one of the most critical functions motor oil performs. When the additive package can no longer perform it, the acids attack bearing surfaces, etch cylinder walls, and corrode valve train components from the inside. Yet drivers see that light and think, I'll handle it after the weekend. They think, it's probably fine for another 1,000 miles. According to Blackstone Laboratories' 2023 Oil Analysis Report, compiled from thousands of real engine oil samples, engines driven 2,000 miles past their oil life warning showed 31% viscosity breakdown and iron content increases of 340% compared to on-schedule samples. Iron in oil is wear metal. It is microscopic metallic debris generated by surface-to-surface contact inside your engine. A 340% increase means your engine is actively consuming itself, while the service light you dismissed sits there glowing on the dash. There's no margin worth protecting when the cost is bearing surfaces and cylinder walls. When the monitoring system says it's time, the chemistry of your oil has already reached its limit. The correct response is same-week service without exception. What you now know that most drivers never will. You just worked through 8 failure modes that the automotive service industry profits from treating rather than preventing. The double gasket that hides in plain sight, the cold oil that poisons fresh chemistry before you've driven a mile, the aeration disaster hiding inside a half-quart overfill, the dry start that inflicts a lifetime's worth of cumulative wear in 3 seconds, the post-change check that saves you from driving away a quart low, the micro tears that turn a 3-second lubrication step into a persistent leak, the stripped threads that end in an ejected drain plug at freeway speed, and the warning light that is never a suggestion. Which of these have you experienced firsthand, or watched someone else learn the hard way? Drop your vehicle's make, model, and year in the comments. Let's build a real database of what actually happens out there on real cars. Before you go, if this kind of engineering-backed content is what you've been looking for, subscribe right now. We don't cover car care, we cover car science, and there's a lot more of it coming. Speaking of which, up next on your screen, 50 engines tested head-to-head, 0W20 versus 5W30. The results are not what the oil companies want you to see.